Hey there. So today I watched a very interesting math problem on YouTube given by Math Beast. And you can see the screenshot here. So you are asked to solve a quite intricate polynomial equation. You can just go to his link and follow the way and the steps to find the exact solution for that. So I think this problem is quite fascinating because it's not only show you the way to solve this particular problem, and we can actually generalize a little bit more about this type of construction if you have followed the entire video. I'm going to skip some of the details and just expand based on his content, and I will see as the number of power goes higher and higher, what we can find about the distribution of all the roots. Because the problem he was dealing is only concerning about, I think, the real roots. But since the polynomial is of very high power, so it's very likely that we can have roots spread all over the complex plane. I happen to have this code written just to simulate his results, and we will see how we can find the solution for this type of polynomial once we raise the power to even higher numbers. Okay, let's first just follow and using solve function to find all the roots. Okay, so these are the roots, and two of them are kind of easy. One plus square root of 5 over 2, and the other is square root of 5 minus 1 over 2, and take a negative of the expression. So these two numbers are not arbitrary because they are closely related to either the golden ratio and Fibonacci sequence. And we can just use, so this is a very well-known analytic expression to generate all the Fibonacci number if you have the two terms ready. And you just plug n here. For n equal to 1, equal to 2, and equal to 3, and so on, you will have different terms for Fibonacci sequence. And that's exactly how the author constructed this solution, okay? But besides these real solutions, we also have other expressions which looks a little bit scary because they are wrapped in these like root expressions. If you happen to know anything about a Galois theory or splitting fields, you will know these are actually valid, very good solutions, just like the analytic expression we see here. Because once you expand the number to a different type of fields, you add different roots of polynomials, you can actually have very nice expressions for linear factorization, just like x minus a, x times x minus b, and x times x minus c. And these numbers can be, very complicated, but these are actually valid. And let's see the numeric values about the length or the modulus of this complex number. And if you apply the ABS, the absolute value or normal value function, to these complex numbers, you will see these numbers are not apart very much. And after we raise the power of this polynomial, we actually will see some patterns for them. And that's what we are going to talk in the asymptotic behavior. So let's have these roots, and we can just plot them. So these are the roots. And if we get rid of this guy, for the other roots, it seems it sits on a very good circle, right? It looks like everything is on a circle, which is kind of expected because that's the radius or the modulus of these complex numbers. So that's basically the length of the complex number, or it's the distance between this point and the origin. So these numbers are kind of close. Okay, so it's expected for them to sit on the circle. And besides that, you can also see that they look like sit equally spaced on the circle, like regular polygon. So this is a kind of a intuitive and qualitative observation we have through the computation. The factor function to factor this polynomial. And it's not to our surprise that there is a factor like this. So this is one of the reasons that the author point out you can use Fibonacci numbers to solve this problem. And then let's look at the other part. So this part is kind of scary. You have a lot of terms, okay? But if you look closely at the absolute values of the coefficients of this polynomial, it's 1, 1, 2, 3, 5, 8, 13, 12, 21, 34. And you add up two numbers. 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 5 is 13, and so on. So the coefficients you have here is absolute values are exactly the Fibonacci numbers. Okay, so this is what we have, and if we want to check Fibonacci number 11, it's exactly 89. So this is the coefficient. And let's see 10. It's 55. So this is the 55. Okay. And we can just kind of generate a general expression based on the rules here. So in this case, this polynomial is generated by this rule. Is generated by this rule. So the first item is, for example, is the ith. For example, this is 11th Fibonacci number, 89. And this is 11 plus 1. And this is 11. And this is 12. So 144. Okay. So this is the rule that generates this polynomial. So we can use that. And instead of using factor to generate the factorization for this polynomial, because we assume this one always has this polynomial always had a factor about x squared minus x minus 1. So we are confident to do polynomial quotient and not worry about the remainder, which is also always to be 0. So this way we can handle very large polynomial without any issue. Otherwise, we'll have some of the performance issue based on the factor. So we can give it a pretty large number and see what do we have. So assume the power is 37. And this is the 37th Fibonacci number as the coefficient, and we can generate a polynomial like this. And let it divide x squared minus x minus 1, because we focus on this part, and we always know this part will be part of the factorized list. So let's just take a look at it. Okay. So this is the polynomial we have. Okay, and we can solve that. So this is the solution for the polynomial, and this is the asymptotic behavior we are looking for. All the blue dots are preset points, because they are generated as background. Because what I expect is as power goes higher and higher, these yellow dots will overlay the points that I preset. So instead of blocking your view, I just make these preset points much larger so that they can work as the background for all the roots. And we can see that as the points at the power goes higher, and we only choose this number as odd number, we will see all the yellow points will sit exactly at the center of the blue points. And that's with the expectation we have from the beginning. Okay, that looks like magic. And what's the preset point I have? So the preset points are very simple. These are the points that's sitting on a regular polygon. And this polygon has some of the very interesting property is that the radius, it's just like this. The radius. That's the first point on the polygon. Second, third, and they are equally spaced. Okay. The last one is 15. So 15 and 1 are symmetric about x-axis. Okay. And there is initialization angle because it's for instance you have a square. You can have a square like this, or square sitting in a circle like this. So in this case, the initialization angle is 45 degrees. Okay. In my case, the initialization degree is 180 divided by the number of power. So in this case, it's 37 points. 37 points. And this point is 180 divided 37. So this is the regular polygon that I generated along the circle. And all the points just sit very tightly to the center of this regular polygon. And why is that? So here we need to use Binet's formula and the formula for geometric progression at the same time. Okay, here is the reason. As the polynomial goes higher and higher a power, we have more and more terms. So this polynomial should look like 1 minus 5x plus 5 square x square minus 5 square x cube plus to 5 n x n. N plus 1. N plus 1, yes. N plus 1 equal to 0. So the reason is once the Fibonacci number gets bigger and bigger, it's closer to 5 to the power of n, because from the Binet's formula, this part is of the magnitude less than 1. And anything less than 1 to the power of a higher n, as n goes to infinity, this term goes to 0. So this term will be smaller and smaller. And if we only look at the absolute value, which is only determined by the first term in the Binet's formula. Okay, so this is the formula we have. And let's go back to the formula for sum of geometrical progression. Geometrical progression says that if a is equal to 1 and z equal to phi x, phi times x. But we also need to put a minus here. So this in this case is z equal to minus phi x. Okay, and the first term is z to the power of 0 is 1. Okay, so this is the formula that we can use to compute the root for this higher power polynomial, because it will turn into, for example, if this is a 36 as a power, okay, according to the formula, that's n plus 1, that will be 37. Okay, so what we have here is, because 37 minus 1 to the power of 37 is minus 1. So eventually we'll have this thing, 37 plus 1 equal to 0. And with z equal to, here, because we already moved the minus sign to the outside, so we can just write z as phi x here, right? Because the minus sign is already moved out. So this thing will give you exact solutions for all the points on the regular polygon. These are the blue points, and we can find it easily just by using Euler's formula. E to k pi. Minus 1 is ei to k pi times ei pi. And for k is integer, k equal to 0, 1, 2, 3, 4, 5, and so on. Therefore, the points will be, the blue point will be it's 2k plus 1 pi over 37. So these are the times I. So these are the points. But don't forget that this is for phi x, where the phi is equal to 1.618, which is the golden ratio. So the x, the blue x, is actually 1 over phi times this value. So that's why we have all the points getting closer and closer to the blue points, which are defined by this formula. Okay, so this gives you a very intuitive and a quick solution for this type of problem if we have really large n or really large power here.